Now we're going to examine the first way that we can calculate delta H for a reaction. As I said previously, there's going to be 4 ways that you can calculate delta H, and it depends on the information that you're given. The first way that we're going to use is to use bond dissociation energies. And this goes on the principle that when there's a chemical reaction, what is happening is there are bonds that are broken and there are new bonds that are formed. And it's the overall energy difference that's going to lead to it being an endothermic reaction or an exothermic reaction. In order to break a bond, that's going to require energy because the molecule is stable, the atoms are being held together, sort of like there's chemical glue holding them together, and we need energy to break them apart. So that's going to be an endothermic process. When we form bonds, we're stabilizing molecules. So if you think of a hydrogen atom on its own, it's unstable with its one lone electron, but when it bonds to another hydrogen, overall, the energy of the system is lowered and there's energy released. So that process is exothermic. The amount of energy involved in these processes is equal and opposite. So whatever energy you require to break a bond is the amount of energy that you release when you form a bond. And what we're going to be looking at is the overall net energy. So the formula for finding the delta H is to take the total amount of energy to break the bonds and subtract the total amount of energy released when you form the bonds. Now, when you're using this formula, you're not going to need to think about whether something's exothermic or endothermic. That's taken into account in the formula. We take all the endothermic and we subtract all the exothermic, so the sign is built in. Now this table, which can be found in your textbook, gives us some key bond enthalpies that we'll use to determine the overall enthalpy change of a reaction. You'll notice that most of the bonds are ones that are involved in organic reactions. A few things to note: it's really important that you know whether or not you've got a single, double, or triple bond between two atoms because there's a significant difference in the amount of energy. And the amount of energy in a triple bond isn't just triple the single bond. Okay? It's actually more significant because you've got those pi bonds in there. So this is particularly important when you're looking at diatomic molecules. And what I'm going to encourage you to do anyway is draw the Lewis structures. But when you're drawing the Lewis structures, you even do need to do that for diatomic. So for example, in N2, it's actually got a triple bond. And if you drew it, you'd be able to see that. Okay? And O2 is also. You can see on my screen the ones that are in red, those are diatomic molecules. So they're kind of highlighted a little bit, but it's more difficult for you to see that in your notes. Now these are going to be average bond energies. So for example, a carbon-carbon bond, depending on the molecule, it might vary slightly, okay, but this is the overall average of all the bond energies. One thing to note as well is that for the carbon-oxygen double bond in carbon dioxide, you're going to use 799 rather than 745. So let's look at some examples on how we would calculate delta H. This first reaction, we've got H2 plus Cl2 going to 2HCl. And put a diagram of the molecules here, because it's important that you visualize the molecules or draw structures so you know which bonds are being broken and which bonds are being formed and how many of each. So in this balanced equation, I require one hydrogen molecule, so I'm breaking one H2 bond, and I'm breaking one bond in a Cl molecule. For the HCl, there are two of them, so I am forming two HCl bonds. So the delta H is going to be the energy of the bonds broken minus the energy of the bonds formed. So it's a matter of looking up the values in the table and being really careful when you transfer the numbers. And being really careful when you add things as well. So the H2 bond is 436.4. The chlorine-chlorine bond is 242.7. Then I've got 2 times the HCl bond, which is 431.9. So when you sum up the bonds broken and you subtract the bonds formed, you're left with 184.7 kilojoules. Okay, so in this case, it's an exothermic reaction. So if you look at it, the energy that was required to break the bonds is lower than the energy that was released when we formed the new bonds. So when we say it's all about the net energy difference, that's what we're looking at. Okay, we require a certain amount of energy, we get back a certain amount of energy. Okay, whichever is greater is going to decide whether it's an endothermic or exothermic reaction. For this next one, we've got N2. So like I said, you need to draw the Lewis structure, and if you draw the Lewis structure, you'll see that it's a triple bond. Okay, then we've got 3 HH bonds, and those ones are single. And then in this case, NH3 is ammonia, and this is the Lewis structure for it. So when we've got 2 NH3 molecules, we've actually got 6 NH bonds. So in this, we're breaking this bond, and we're forming 6 NH bonds. So the delta H, we take the sum of the energy needed to break the bonds, and we subtract the energy released when we form the 6 new bonds at 393 each, and you're left with negative 107.4 kilojoules. The biggest challenge with these, although it sounds minor, is getting the math right. Okay, so you really have to be careful, do it twice, double check, and make sure you've got it. Okay, on the handout that you have, there are some extra practice with the answers there. Okay, they're a little bit bigger reactions. You need to draw the Lewis structures in order to be able to handle them. When you have an organic reaction, there's 2 approaches that you can take. You can look at destroying the entire molecule, so you can break all the bonds and form all new bonds. Or if you look really carefully, you can look at which specific bonds were broken and which ones were formed. Personally, I find it easier to just count all the bonds so I don't miss any. But how you approach that is up to you. You will get the same answer whichever approach you take. And that concludes this lesson.